Good afternoon, Amherst. Welcome to what promises to be the last video for new material for school year 2020. That's the one we've been looking for. Organic reactions. Okay, so the majority of organic reactions that you're going to be responsible for are going to be ones you simply need to recognize them. However, there are a handful that you're going to actually have to be able to balance or manipulate, predict products, name reactants, name products, all that kind of stuff. So we'll start with those. First one, substitution reactions. Now, substitution reactions occur when you take a saturated hydrocarbon and you want to put something on there other than hydrogen. So saturated hydrocarbons have all single bonds, so you can't just break open double or triple bonds, so you undergo substitution reactions. Saturated single substitution. So the rules of the game are one at a time. You rip off one hydrogen and you put one atom on there. You can't just double up. So here's an example. If I have C2H6, it's ethane, and I want to put a chlorine on there. Well, chlorine's diatomic, so it comes to Cl2. What are you going to form? How does this work? So here's ethane, carbon-carbon single bond filled up with hydrogen. Here's chlorine, double-double here. You're going to pop off a hydrogen, put it there where this chlorine is going to go on over there. It's kind of like a double replacement reaction if I was doing inorganic chemistry. So this one comes off, this one goes on. This one comes off, this one goes on. You're switching places. So the chlorine is substituted in for a hydrogen. Now, it doesn't matter where you put it. These are 6 equivalent spots, to tell you the truth. They're all the same. It's just easiest to show it on the end. So here you go. You have what is then chloroethane and hydrogen chloride. You could call it hydrochloric acid, but it's not dissolved in water, so more technically it's hydrogen chloride there. But I would accept either name. Okay, so one in, one out, one at a time, saturated, single, substitution. You'll need to be able to do those types of reactions. Ethane plus chlorine, chloroethane, hydrogen chloride. All right, so you could call that reaction substitution. Since you put chlorine on there, you could call it chlorination. And since chlorine is a halogen, you could call it halogenation. Those are just all examples of like more specific names for this particular substitution reaction. Next, addition reactions. Addition are that's a reaction for an unsaturated hydrocarbon. So you've got double or triple bonds in there that you can break open, take that double bond, boom, break it open. Now you got a half bond here, half bond there, and you can stick things on there. You can make that hydrocarbon bigger, heavier. So what if I had something like ethene, E-N-E, and I want to put some more hydrogens on there? So here's ethene, it's got a double bond here. I'm going to break open that double bond. Here's hydrogen, I'm going to break open that bond. And that half bond that's going to go here, and half bond here, and this half bond, and this half bond, we're going to put them together. So break it open, here's a half bond, here's a half bond, here's a half bond, here's a half bond. Put a hydrogen there, put a hydrogen there. You just made ethane. So you took your unsaturated hydrocarbon and you saturated it. Ethene plus hydrogen goes to ethane. Now, when you put more hydrogens on there, you're making the molecule heavier. It's still a nonpolar molecule, but you're hydrogenating it. So if you look, for example, at your margarine-type compounds, they are partially hydrogenated vegetable oil. So you take that oil, you put some more hydrogens on there, you put some more hydrogens on there, you put some more hydrogens on there. It starts to drive up the formula weight. It starts to drive up the strength of the intermolecular forces. It starts to drive up the boiling point and the melting point. You go from being what is more liquid to more like a solid. Technically, I guess margarine isn't a true solid. It's more of an amorphous solid. It's got characteristics of both solid and liquid, but it's certainly thicker than the oil you started with. So I could call this reaction addition, which is its most proper name because I added hydrogen on there. And I suppose I could have called it hydrogenation. All right, next one, esterification. We've talked about it. You're going to make an ester. So to make an ester, you need an alcohol. It's generally a primary alcohol and an organic acid. The alcohol forms the prefix of the ester's name and the acid forms the suffix. So primary alcohol plus organic acid is going to make an ester plus water. It's a dehydration synthesis. We did this one. The acid, you're going to lose the hydrogen. That's what acids do. The alcohol is going to lose its hydroxyl group. That's going to form the water. There's your dehydration. And then you synthesize the rest of the molecule together. And the prefix came from the alcohol and the suffix came from the organic acid. So, for example, if I take one propanol and butanoic acid, I'm going to make propylbutanoate. Butanoic becomes butanoate. Propylbutanoate. And then you're going to have water. So Here's your 1-propanol, take the OH group off of there. Here's your butanoic acid, I wrote it backwards because it's just easier to see. Take the H off of here, the OH off of there, form your water. Take the remaining pieces and stick them together, these 3 carbons, go on the other side of this oxygen. So you go, here's your propyl, and here's your butanoate. Okay? Even at the Reagents level, esterification reactions are pretty popular. So you could have called this esterification. It's an example of dehydration synthesis. Next, number 4, combustion of a hydrocarbon. Now we know reacting with oxygen, that's an oxidation reaction. It's technically a redox reaction. But combustion is something that you'll see. We burn hydrocarbons. We use hydrocarbons as fuel, all kinds of stuff, whether it be methane or propane or butane or octane or dodecane. We take hydrocarbons, we react them with oxygen, and we form carbon dioxide and water if we have enough oxygen. But if your furnace isn't working well and it has limited supply of oxygen, you might form carbon monoxide, or you might form soot, which is just plain carbon, which is what my oil burning boiler was doing over the winter. So, very dangerous, no good for you. Complete combustion, you're going to form carbon dioxide and water. Incomplete combustion, you're going to form carbon monoxide, maybe some carbon and some water. Okay? You're going to have to be able to balance complete combustion reactions. You're going to have to recognize incomplete combustion reactions. So let's practice a couple of these. We've done these before, but let's do them again. They bear repeating. In a complete combustion reaction, sometimes they're simple, and sometimes you end up having to use a fractional coefficient and then double everything. So here's the simplest hydrocarbon. Methane plus oxygen goes to carbon dioxide and water. I've already done it, but basically carbon, hydrogen, oxygen, before the coefficients were in there, you had 1, 4, and 2, and 1, 2, and 3 respectively. So in a combustion reaction, when you balance, just work down. The oxygen gets split between both products, so do it last. I start with the carbons. You got 1 carbon, you got 1 carbon, good to go. 4 hydrogens, 2 hydrogens, you got to double that and make it 4, so you put a 2 here. Well, that gives me 2 plus 2, that gives me 4 oxygens, so I need to double this and put a 2 there. Easy peasy. Balancing by inspection. But what about when I end up having an odd number of oxygens over here? And it makes an odd number of oxygens over there. Okay, we've done these in class, but just because it bears repeating, here's a more quote-unquote complex example. What if I have C2H6? It's the next alkane plus oxygen. Forget the coefficients for a second. Once again, if I look at balancing it, before the coefficients were in, I had 2, 6, and 2, and then I had 1, 2, and 3. All right, so start with your carbons. I need 2, I put a 2 there. All right, it's going to affect my oxygen, but save oxygen for last. I have 6 hydrogens. I need to make that 6. I need to put a 3 here. Now I have 4 and 3. I have 7 oxygens. How do you get 7 oxygens if they come in pairs? Tough to get an odd number when they come in pairs. So what you do is you say, well, 3.5 pairs would give me 7. So if I put a 3.5 there, that would work, except you can't have 3.5 oxygens. So then to get rid of that half, you double all the coefficients. So this 1 becomes a 2, this 3.5 becomes a 7, right? This 2 becomes a 4, and this 3 becomes a 6. And those can't be reduced. 2, 7, 4, 6 are the lowest whole number coefficients. That's the way you do it. So let me just say that again. If you need an odd number of oxygens, use a half coefficient in there. Like 5, well, that's 2.5. All right, 7, that's 3.5. 9, that's 4.5 pairs. And then double all the coefficients. We did it before, but you'll see it again. And you'll see it balances out. Next example. Things to recognize. Organic reactions that either in word form or diagram form, you're not expected to balance them, but you are expected to recognize what they are. So let me fix my pages here. First one is fermentation. Fermentation. So you're going to take some aqueous sugar in the presence of yeast. Yeast contains enzymes, particularly zymase, and yeast eats up the sugar and it metabolizes itself into ethanol and carbon dioxide, booze and bubbles. Sugar dissolved in water in the presence of yeast, which is zymase acting as a catalyst, forms ethanol, that's the alcohol of liquor, and carbon dioxide. Beer and wine are naturally carbonated. Now, there are all kinds of industrial processes where they remove the CO2 and then recarbonate it later. I'm not going to worry about that too much. Just understand, if you see zymase, if you see yeast, If that's acting as a catalyst, you see ethanol, that's fermentation. You need to recognize it. I did see one Rxns question where they made you balance it. It wasn't hard. Basically, if you go through this process, you need to put a 2 and a 2 here and split the carbon up, because glucose C6H12, well, ethanol has 2 of them, and carbon dioxide is 1 of them. So if I put a 2 here and a 2 here, that doubles up my carbon here. There's 4, there's 2 more here, that's 6, which, hey, that fixes my hydrogen, that fixes my oxygen. Good to go. I was surprised when I saw it, but it's a fairly simple balance by inspection. Next one, polymerization. Polymers are huge. In the history of humankind, we've had what? The Stone Age, the Metal Age, and then the Polymer Age. I guess we've moved into the Information Age now, but polymers are plastics. They're a big problem on the planet right now. They've got enough plastic in the ocean. It's like the size of Texas floating around out there. We need to figure out what to do with polymers because they tend to last for a long time. But basically, they come in 2 varieties. You have addition polymerization and condensation polymerization, and you just need to recognize the difference between the 2 of them. So in addition reactions, you would break open double or triple bonds. It's the same deal here. In condensation, the first word I think of is water, so you're going to remove water through a dehydration synthesis. Okay, it's pretty similar to esterification, but it's a repetitive process. By the way, if you repeat it with an ester, you form a polyester. Okay, so take your double bond, break it open, put a half bond there, put a half bond there. Take another one, do it again, and then stick the pieces together. So you're literally just taking another one, putting it here, and this chain can go on and on and on and form hundreds or thousands of molecules. Here, I have something that's got an OH hydroxyl group and something with an H on the end of it, and I remove that water and I put these pieces together. It's a dehydration synthesis and it's a repetitive process. Just recognize it. So in a formula, you'll see this in the worksheets, addition polymerization looks like, hey, I've got ethene here, I've got N of them, an indeterminate number, but it's a big number, 500. I'm going to break it apart, I'm going to make one chain that's 500 links long. Each piece of the chain is called a monomer. Take 2 monomers, put them together, now you've got a dimer. Put another one on there, now you've got a trimer. You can continue this process until you have an indeterminate number of them. They are a polymer. Now, big, long polymers are like big pieces of wet spaghetti. They're like noodles. They're kind of, they knot up and they have a little bit of flexibility to them. That's why plastics can bend a little bit. So it looks like this in formula. Big N out here, lowercase n here, but they don't have to be capital and lower. But you'll see there's ethene, and this is the building block for polyethene. Monomers connect to form dimers or trimers until you get polymers, which are long string molecules that are bendy and stretchy, and you can do all kinds of stuff with them. So ethene turns into polyethene, which used to be called polyethylene. You may have heard that before. But you'll see on recycling things on plastics being bendable, HDPE, and they usually put the triangle, okay, and the number inside. So if you grab a typical soda pop bottle, the top, the dense plastic, that's HDPE. The bottle itself, the clear stuff, that's polyester. Yes, the same stuff you can make like clothing and whatnot out of. So HDPE, you'll see it on recycling labels. There's low density polyethylene as well. It's a little bit, softer, bendier. Condensation polymerization. Basically, it looks something like this. You pull an OH off of something, pull an H off of something. Here's ethylene glycol, 1,2-ethane diol, your antifreeze. So when your antifreeze starts to break down, it gets hot and whatnot, it helps this reaction occur. You start putting these things together. Now this is starting to look a little bit like dihydroxy ether here, and it's going to be bigger, and you can put another one on there. Okay, you're going to remove the water, stick another one, and now it's starting to get bigger and bigger and bigger and bigger. And this can go on and on and on. So your antifreeze is breaking down, it's getting thick, it's getting gloopy. Every now and then you have to change it. But if you are putting pieces together by removing water in a dehydration synthesis repetitively, that's an example of condensation polymerization. So you remove H from one piece, OH from the other piece, put HOH together, remove the water, that's your condensation, and put the pieces together to make a long string that is a plastic bendable molecule. Polyester is an example. Next one, saponification. If you rearrange these 4 letters, you can come up with the word soap, and that's exactly what it is. Saponification is making of soap. It's what happens when you get base on your hand. The oils in our hands, oils and whatnot, those are esters, those are fats. So if you put a base together with a fat, you're going to form a stearate. A stearate is called a soap, and you're going to form water. Bases make soap out of you. That's why they feel slippery. Soaps are known as stearates. You just need to recognize saponification is the making of soap. So why are soaps important? Well, the one end is very symmetric and kind of nonpolar. The other end tends to be ionic, which is uberpolar. So this could be a whole long, 100 molecules, 100 atom chain in here. But this side is largely symmetric and nonpolar, and this side is ionic, which is uberpolar. So this side will dissolve things like hydrocarbons, oils, and grease, nonpolar molecules. And this side will dissolve in water, and then you can wash away greasy substances. They emulsify those things. They grab a hold of both polar and nonpolar substances. Next one. It's an industrial process. It sounds bad. Cracking. No, it's not like the crack cocaine drug. It's breaking apart big, long hydrocarbon molecules. If you grab crude oil out of the ground, petroleum, you've got big, long, gloopy, tarry molecules that aren't useful for much other than paving the roads, maybe. But if you want to burn fuel in your car, you need to make some octane. You need to make some dodecane for your diesel fuel. So you need to break those big, long pieces apart. So you're breaking long chain hydrocarbons into smaller pieces, which can then be separated by differences in boiling point through a process known as fractional distillation, which we talked about. That's the refining of crude oil. So you can make things like octane, gasoline, and dodecane from things like tar, La Brea tar pits out in California. Pretty useful for making fuels. And the last one would have been elimination reactions, but I am going to eliminate that from the curriculum because I have never seen a question, ACS or Regents, on that. So with that, we're done. That is the last lesson on new material for the year. I will post this momentarily, and then beginning on Monday, I will post a practice ACS thing that I came up with last year, and then we'll practice on half an ACS, and then we'll take an ACS, and that will be it, or half of an ACS, and that will be it for the year. I thank you for your time. I'll talk to you soon.